Okay, this is going to be the chemistry review. So this is going to be our chemistry part of our exam review. And I'm going to be talking about everything from the beginning of what we have to the end. So this is actually the fun part with chemistry. Oop, that's not even an atom. But this is something that you've been used to seeing. I don't know which one I'm going to use, but I'm going to use both colors. Basically, for chemistry, if we want to start at the history of chemistry, basically we were to take any object, and if we were to kind of zoom in to one particular region and keep zooming in, here's my magnifying glass, and zoom this in even more, what are we going to see? So if we were to actually look inside that small part, we would start to see, as in the first guy who kind of came up with this idea was named Democritus. And Democritus just kind of believed that everything is indivisible, and as you were to break them down, you have atoms. Those little squiggly marks means that they're sort of moving along or vibrating, and that's, you have your atoms vibrating. And what it is that scientists kind of believe that you have your atomic theory, where inside you would have your atoms. So this is what an atom would sort of look like, and you have bigger atoms just kind of moving around in that little box. Well, and if we were to take one of these, and you will most likely see is something like this, right, in a Bohr model. So everything like in here, this is your protons and neutrons inside, and sometimes you will have these things that are flying outside. Well, what are these things? Well, these are your electrons. So this little kind of circular orbit, this is named after some guy, Niels Bohr, who came up with this idea. And Bohr basically got this idea from our solar system of how our planets revolve around the sun. So this is the sun, and then you have your planets kind of revolve just exactly like your electrons moving around the nucleus. So how do we draw these Bohr diagrams? If we take an example, say boron, you want to start by having the nucleus. This is in the middle, and on the outside you have your rings. Remember, there's your 288 rule. That rule represents the number of electrons that can occupy. So in the nucleus in the middle for boron, atomic number is 5. So this is your atomic number. That means with atomic number 5, you're going to have 5 protons. And 5 protons, and then you're going to have neutrons of 10.6 neutrons. You might be wondering, how did I get this? And we're going to talk about that in a bit. But once you have this, then you're going to fill in the number of electrons. So because we have 5 protons, we're going to have 5 electrons. So the first shell is going to have that. I'm going to change colors. Boom, boom. And then I'm going to have another shell. We're going to have 1, 2, and 3. So in total 1, 2, 3, 4, 5. That's my boron. That's, again, this is the Bohr diagram. Once we have this diagram, you have seen all this. This one usually just works for the first couple of rows, because once you get too big, it gets a little bit complicated. So if we move on for these Bohr diagrams, we know that there are 3 components of a atom, or parts. We know that there's something called the pros from the video, called protons, something called the neutrons, and then your electrons. All of these ones are found in an atom, and you know that the first 2, this is going to be found in nucleus. And these ones actually are what makes up your atom's weight or mass. So this one makes up atom's mass. Why is that? Well, that's because the protons, P plus N, this is actually going to be equal to your atomic mass that is found on your periodic table. The electrons, on the other hand, actually doesn't really weigh that much. And this is found, instead of in the nucleus, it will be found outside from the nucleus. Okay? And all this stuff all these three components are found in all atoms: protons, neutrons, and electrons. So again, protons and neutrons found in nucleus, they make up the atom's mass, and electrons are found on outside. So why is this important? Moving on, let me align this. We have something called a periodic table. This is really important because in a periodic table, I'm just going to draw a rough sketch of a periodic table. And you should have something like this already. A periodic table, it is a line. If we were to just take one out here and zoom in, this will look like this. Here's my oxygen. It has an 8 at the top and 15.999 at the bottom. What these numbers represent is that the 8 is going to be your atomic number. This is going to be your atomic mass. Okay, and why this is important is that the atomic number is also the same as your number of protons. This is the same. If you look at the same diagram from before, it is exactly what's inside. By having a neutral atom, the number of protons is going to be exactly the same as number of electrons. So this is just my little writing for electrons. So that by that one number, we can determine the number of protons and the electrons. Well, what can the atomic mass tell us? So atomic mass, remember this is found in it's found in nucleus, where it's the number of protons plus number of neutrons. Okay, so if we have that, we have the atomic mass 15.999. This is equal to number of protons, which is 8, plus number of neutrons. Well, we don't know what number of neutrons what we have here, but we can actually use math equation to figure that out. So I minus this 8 minus this 8. So basically, number of neutrons in this oxygen is going to be 8. And that's basically how you read a periodic table for one single element. So this is going to be my symbol, atomic number, atomic mass, and that's it. What else can we find from the periodic table? Actually, a lot of things. So the first thing you need to know is that you're going to see numbers at the top. These ones are going to be your groups. So I'm just going to make this here and in here and drop this. That's my oxygen, fluorine. So these ones are all going to be your groups. And going across each of these periods here, these ones are called periods. So they go sideways. Okay, so this is be period 1, period 2, and then this is going to be period 3. Okay, and so forth. And what you can see aside from these groups and periods is that each of these groups actually have a special name. So the first one is called alkali. Second one is called alkaline earth. And then the last one we're going to talk about is called the noble gases. One beside it is called your halogens. And the last one is chalcogens. So these are your family names that you need to know. And why it's important to know them, because each of these families are different, like different teams. They have different properties. This alkali is very reactive. So basically, if you were just to put this in water, it will go crazy and it will react. What else can you find out from this periodic table? Well, there's actually more stuff. So if you remember, if you draw this step ladder, I'm going to use a different color step ladder, you are actually going to separate this periodic table into something called, on this side, this is going to be your metals, and on this side, non-metals. So that's all on this side. Well, you might be wondering, what about these ones that's surrounding the ladder. These ones are called metalloids. So why do we need the metals, nonmetals, and metalloids? Well, they all have different properties. So if we look at the metals, the properties of metals is that, number one, it is malleable. What does that mean? It means that if you were to take a piece of metal, take a hammer this down, you can actually create and bend it and flatten it into a really, really flat point. It won't break. It's not brittle. Okay, that's one property of metals. It also conducts electricity and heat. If you think about our elements on our stove, why we use that particular type of material is that once it gets heated, well, number one, that is a piece of metal. That means that it can conduct electricity. By conducting electricity through this element, it will conduct heat to make it really hot. And the next one is ductility. This one is a funny word, but basically you can take your big piece of metal and spool it and spin it into a piece of wire. So this is just my piece of wire. So you can spool this and into a piece of wire. That's ductility. And the last thing is that anytime you see anything metallic, you know there's luster or shine. So that's metals. What about nonmetals? Nonmetals, just like what the name suggests, are not metals. And their properties are completely different because nonmetals will have no luster, no shine. They're brittle. That means that if I were to take a big hammer and hammer some sort of nonmetal, what's going to happen? It's going to go into pieces, shatter, boom. And then what's the last one? They're not non-conductors. You cannot put electricity through non-metal, and that's it. So that's non-metals, no luster, brittle, non-conductors. You can't put them into wires. They're not malleable, completely opposite from metals. Well, what about my metalloids? Well, these ones are just the in-betweens. So some of them will have both properties of metals and non-metals. Some of them will have some luster. Some of them can conduct electricity, but not all. Electricity. And that's it. So that's what you have all found in this periodic table. So again, this periodic table arranges into your groups, your periods, different names: alkaline, alkaline earth, chalcogens, halogens, noble gases. And how you read them is your atomic number, you have your atomic mass. Just make sure you understand all this stuff. Okay? And then this actually leads into, well, what if we have something like H2O? Is this an element or a molecule? Well, this is going to be a molecule because it has 2 hydrogens and 1 oxygen. When they combine together, it makes 1 molecule. Well, what is an element then? An element is anything, any one of them you find on the periodic table. So if you have something like P, phosphorus, this is an element. If you buy a balloon at Safeway and those are helium balloons, inside the helium balloon is just all heliums. This balloon is not laughing. This one is, inside here is an element because they're all helium. You don't have any mixtures. Okay, so that's what defines an element. So how do we do bonding? Because this is going to lead into our next step called bonding. So if we have something like Mg and F, what is the actual formula? Is it going to be MgF, Mg2F, MgF2? Well, which one is it? To determine this, you want to draw the Bohr model. So Mg, if I were to draw this quickly, you're going to have 1, 2, 3, 4, 5, 6, and finally, you're going to reach to the last outer shell. You're going to have 2 electrons on the outside shell. Fluorine, if I were to draw fluorine, you're going to draw and find out that on the outside shell, you're going to have 1, 2, 3, 4, 5, 6, 7. So why this is important is that all atoms, they want to achieve 8 electrons or none at all. So since this one has 7, it needs to gain 1. So where is this one going to get the electron from? So if you look at the Mg, this one has 2 electrons on the outside. So it needs to lose 2 electrons. What's going to happen is that one of these ones is going to go here. Well, now this one is full. Now it has 8. 1, 2, 3, 4, 5, 6, 7, 8. Where is that one going to go? This one is going to go to another fluorine. So I'm going to draw my last fluorine. And that's where that's going to go. So out of this, how many magnesiums did I use? 1. So I'm going to write Mg. How many fluorines? I have 2. So MgF2. You might be wondering, well, is there a shortcut? Because I don't want to write all these Bohr models. Of course, there's a shortcut. So bonding. This one is going to depend on your periodic table. So if you take up your periodic table again, what you need to know is just ignore the middle part, the transition metals. Ignore this. You're going to have this 1, 2, 3. Oh, I don't know if I'm going to have enough room here. And I'm just going to squeeze one more in here. So you're going to see at the top that this is going to be group 1, 2, jump all the way across to 13, 14, 15, 16, 17, and 18. What those numbers represent, the 1 represents that 1 electron on outside shell. So it doesn't matter if you have hydrogen, lithium, sodium, potassium, rubidium, any one of these ones at the last outside shell, there's only 1 electron. Moving on to the next one, this one has 2 electrons on the outside shell. This one has 3, 4, 5, 6, 7, and 8. 8, this one is happy. That means it doesn't need to take in any more. So if I were to select any one of them, I'll select calcium and say number 16, sulfur. What's the ratio? Well, I know that in calcium there's 2 electrons on the outside shell. So if I were to do a shortcut here, I know that on the outside of calcium there are 2 electrons. What about sulfur? I know there are 6 electrons, so I draw sulfur shortcut, not following my rule just because of bonding. 1, 2, 3, 4, 5, 6. There's 2 left over, so this one is going to go here. This one's going to go there. Now this one has 8, so this one's happy. This one has nothing, so my ratio is that I have 1 calcium for every 1 sulfur, and that's how you bond. So basically, for all your bonding, this is how you want to do it. And I think that's pretty much it for the chemistry unit. The last thing is for the physical and chemical change. Basically, chemical change is changing the properties. So one example here is rusting. because if you take a piece of metal, when you form rust, it actually takes and eats a bit of the metal away from it. You can't take the pieces of rust and magically change it back into your metal. So that chemical property change is a chemical change. Some tricky physical change are, say, salt in water. Even though it looks like you have changed the property of water, you really didn't, because once you put your water and salt in, if you let it just evaporate, you will have your salt at the bottom. That means that the water stayed as water and salt is left at the bottom. So physical change, the properties do not change. Chemical change, you're changing the properties. And that's basically it for your chemistry unit in a nutshell.